I do want to add, from what I said at the beginning of lecture A, that in doing one chapter a day, I think you can definitely handle it. Because a lot of it's going to seem pretty familiar. Like, for example, there's going to be factor rings just like there were factor groups. Okay. Chapters 12 and 13 are pretty short. 15 and 16 are not too hard. 17 gets a little longer and harder. 18 to 19 is not too bad. There's a review of vector spaces. It's when we get to 20 that things get tougher. Okay, start talking about something called extension fields, and that's a pretty tough subject. But I think at first year you definitely can handle one chapter a day essentially. Look down here. This was a property not listed in the reading. Down here at the bottom, you might want to write this down. It was in some exercises that I'm going to assign. Given A, B, and in an arbitrary ring R, and M and N that are integers, define MA. Should you say M times A? Should you say M dot A? It's probably best just to say MA, where you realize A is a ring element, M is an integer, to be the sum of A to itself M times. This is not the ring multiplication. It's more like a scalar multiplication, so to speak, where M is a scalar, except it's an integer scalar. That's consistent with what we did with groups. A to the n meant A times itself, n times, n factors here. And even with groups, we did write things when we used additive notation, like NA, where n was an integer, to mean A added to itself n times. N summands is the official word. But it's a little bit more confusing with rings, because we've got a ring multiplication. This is not the ring multiplication. From that definition, you can derive the properties you see down here at the bottom. These are not too hard to prove. Let's look at the proof of one of them. For example, the book does put a dot there, but don't say dot. Just write it there. Okay. This means AB added to itself m times. I guess I am assuming m is a positive integer here. Sorry. And then there are positive integers here. You can make a definition for negative integers as well, but I'm not doing that really. This is AB added to itself m times. Don't need parentheses there. Notational way. Maybe have like a z plus there. Emphasize m and n are positive. But then you've got the distributive law that does apply to an arbitrary finite number of terms. You can, for example, if I want to prove this fact here, you can factor out the b on the right. So there are m summands in both here and in here. And then by definition, that's MA times B. This is not the ring multiplication. It's A added to itself m times that ring element times B. Does equal this ring element added to itself m times. That's the point. And you can verify something like this too. If a ring has a unity, it is unique. If a ring element has a multiplicative inverse, it is unique. Which seems a little confusing when you think about that example that I mentioned where 6 was the unity of a certain subring of Z10. quick argument for showing the unity is unique is if you assume you've got two unities, one and say 1 prime. If you could show they're the same, that would show it must be unique. And it's a pretty quick proof, actually. It's kind of a little fun little proof. Since 1 prime is a unity, equals 1 times 1 prime, which, since 1 is a unity, equals 1 prime. Done. Since 1 prime is a unity, there's a prime there. And since 1 is a unity. And you might wonder, well, does this get messed up for that example where 6 is a unity of the subring? And the answer is no, it doesn't get messed up. 6 was the unity, acted as a unity on 0, 2, 4, 6, and 8. Not on 1. 6 times 1 is 6, not 1. Mod 10. 1 is acting like the unity there, not 6. Okay? The 1, the true unity, has to act like the unity on everything. And inverses are unique. A subset S of a ring is a subring of R, the ring, if S is itself a ring with the same operations as R, analogous as the definition of a subgroup. To my knowledge, it seems to be the case, and I've looked in my notes, I've looked in my old books, that there's no typical notation for subrings. I mean, I've seen people say, well, why not go ahead and write this? And some people do for a subring. But it doesn't seem to be the case. Our author doesn't do this. And other books I've had don't do this. Maybe some ring theorists do it, just for short. But it doesn't seem to be standard to use this kind of notation for a subring. But I guess I won't mark it wrong if you do, okay? I probably won't, just because it's not a standard thing to do. You just say it's a subring. There's a subgroup test. There's also a subring test. A non-empty subset S of a ring is a subring of the ring if it's closed under subtraction and multiplication. That is, this is not a subtraction there. Dash. That is, if A minus B and A times B are in S whenever A and B are in S. The subtraction is similar to showing with the groups that this kind of thing was in the subgroup when A and B were in the subgroup. So that's where the group operation comes in, is with the subtraction. The multiplication is the ring multiplication, which is not the group operation. But it does have to be closed under multiplication too. Or remember, not all elements are going to be units, and so you can't write B inverse or anything like that. Examples? Well, okay, warning. Here's a warning. It's worth noting. It is possible for S to be a subgroup of R under addition, but not a subring of R. Maybe it's not closed during multiplication. Here's an example. The set of all integer multiples of square root of 2 is a subgroup of the reals, but not a subring. A lot up there, huh? Because, for example, square root of 2 times itself is 2, which is not an integer multiple of square root of 2. So this set is a group under addition. It's in fact the cyclic subgroup generated by square root of 2 under addition. But it's not closed under multiplication. It's not a subring of the reals. Is that going to continue? Can we see what they're doing? They're just purposely dropping things or what? make something? Okay. Hopefully it won't continue too much here. Examples. Let R be a ring and let A belong to the ring. The sum of all solutions of the equation AX equals 0 is a subring of the ring. Should you call this a null space or a kernel? Maybe. Maybe. I'll just say maybe. I'll leave it at that. It's pretty quick verification that it's a subring. It's definitely non-empty because it contains 0, for example. Not doing full proofs here, but trying to give you the idea, at least verbally. 0 is in there for sure. It's definitely non-empty. Is it closed under subtraction? Sure, by the distributive property. Even applied to subtraction. Is it closed under multiplication? Sure, by the associative property. And the fact that 0 times anything is 0, like we proved. Or like the book proved, I should say. It's a pretty quick proof. Subring test. Let R be a ring. The center of R, just like we had a center of groups, there are centers of rings too. Though the book doesn't use the notation Z of R. By the way, the notation Z for the center of a group, I think, is a German thing. I think it stands for center or something like that. It's a German word for center. That's probably wrong. I'm sorry that I mangled the German. Okay. But I didn't see any notation for the center of a ring like Z of R in there, though I suppose you could use that kind of notation. The set of all elements in the ring that commute with everything in the ring. A commutative ring would have a center that's the entire ring. A non-commutative ring would have a center that's not the entire ring. We're talking under multiplication here. It's automatically an abelian group under addition. So you're only focused on multiplication. Is it non-empty? Sure, 0 is in there. Is it closed under multiplication or subtraction? If you assume A and Y are in, X and Y are in the center, excuse me, then you could write this and use both the left and right distributive laws to say ultimately that X minus Y would be in the center. And with multiplication, is it closed under multiplication? Use the associative property a couple times. Plus the assumption that X and Y are in the center. If you want to be picky about all the steps, these would be all the steps to show. To show X times Y is in the center. The associative property plus the fact that X and Y themselves are in the center. It's a mangled Y there. Set of all 2 by 2 upper triangular matrices is a subring of M to Z. And we are talking about integer entries here. Set of all matrices like that. Upper triangular means that you've got a 0 in the lower left corner. The upper triangle in the matrix is up here. Those are the possibly non-zero elements. They could be 0, but they don't have to be. The only thing that has to be 0 in an upper triangular matrix like this is the lower left corner. That's a subring. It is non-empty for sure. It's closed under subtraction. You subtract 2 upper triangular matrices like that, you're going to get an upper triangular matrix because you're going to get a 0 minus 0 in the lower left corner is still 0. And it's going to be closed under multiplication too. You multiply 2 matrices like that, you'll still get a 0 in the lower left corner. You can check that for yourself. Okay? These are pretty quick proofs. All these proofs are pretty quick, sometimes a little tricky. But so far, they've all been pretty quick once you see the trick. Doesn't mean all ring proofs are short and tricky, but so far. Every ring, every commutative ring at least has, with unity, has a group of units, UR, called the group of units of R. UR is the set of everything in the ring, in the commutative ring with unity, that is a unit of the ring, has a multiplicative inverse. It's a group under the multiplication of the ring, is what I'm trying to say. Got that? The elements of U of R are the elements of R that are units that have multiplicative inverses, which would not include 0 for sure. And that forms a group under the one binary operation that's the ring multiplication. You've seen this before, actually. Our old friend, UN. The group of units of Zn is UN. U of Z6 consists of 1 and 5 as a group under multiplication mod 6. For example, U7 would include 1 through 6 under multiplication mod 7. U of Z7. How about the following new kinds of examples? U of Zi, the Gaussian integers. U of Zx, polynomials in X with integer coefficients. U of Rx, polynomials in X with real coefficients. What are the units of those? Without proof, let me just say, I'll let you think about this. U of Zi, the Gaussian integers. This was the set of all complex numbers. A plus bi, where a and e are integers, and I, again, is the imaginary unit whose square is -1. The units in there is a 4-element set, 1, -1, I, -I. It's a group under multiplication. In fact, it's a cyclic group. It's isomorphic to Z4. Group isomorphism. U of Zx contains 1 and -1 as constant polynomials. Does it contain any others? You might think by analogy that maybe it contains x and -x. But no, it doesn't. That's it, 1, -1. It's a 2-element set, and as a multiplicative group, it's isomorphic to Z2. That's also a group isomorphic. X as a polynomial in there does not have a multiplicative inverse, because anything you multiply it by is not going to lower the degree. Multiplied by constant is still a first-degree polynomial. Multiplied by x, it becomes x squared. Could some other constant polynomial like 2 be a unit? No, because if there were a unit, its inverse would have to be 1/2. But wait a minute, a half is not an integer. So that's a 2-element set. URX, however, is an infinite set. 2 as a constant polynomial does have a multiplicative inverse, 1/2. This would be all it'll be all constant polynomials that are non-zero. A would be an R star. That's R take away 0. And in fact, this would be isomorphic to R star. That's a group isomorphism too. But it's an infinite group. But weird things can happen. For example, this thing, which is not constant, and the coefficients are integers in Z8, that happens to be a unit in Z8x. It's got a multiplicative inverse. Scratch your head and you wonder how. I mean, how can I multiply this by something and get a degree that's smaller? Well, it's because you're modding by 8. And so you could get something where you mod by 8 and you get 0 or 1. And it turns out, oh, I figured out the answer ahead of time, but I don't think I wrote it down. It turns out you can solve for A and B in Z8 uniquely in this equation. And there does exist a solution. Maybe I can figure it out in my head quickly here. I think it's 2x plus 3, I think is what it is. Let's try that. 4x squared plus 6x plus 3 times 2x plus 3. We're going to get ax cubed plus, I'm multiplying like ordinary at the moment here, plus 12x squared plus 12x squared plus 18x plus 6x plus 9. What I did there was the first row is 4x squared times both of these. The second row here is 6x times both of these. And the third one is 3 times both of these. But then when you add and mod by 8, you get 0x cubed plus 24x squared is 0x squared plus 24x is 0x. And then 9 mod 8 is 1. You get 1. So this is a unit, and its multiplicative inverse is 2x plus 3. Weird, but true. Fun. You could say weird, but fun. Fun? I think it's fun. This is the fun of rings, actually. The fun of groups was proving like all groups of order 255 are cyclic. Really advanced fun. The fun of rings is modular arithmetic with polynomial rings. That's the fun of rings. All right, to wrap things up, I'm going to introduce chapter 13. Zero-divisors, integral domains, and fields. A zero-divisor, we've already seen their zero-divisors. 3 times 2 was 0 in Z6. 3 and 2 are non-zero. They multiply together to give you 0, the additive identity. In general, a zero-divisor is a non-zero element A of a commutative ring such that there is a non-zero element B so that A times B is 0. And that would also mean B is a zero-divisor too. Also. Note, there are notions, this can be generalized, there are notions of left zero-divisors and right zero-divisors in non-commutative rings, but we're not doing that. I want to keep things as simple as possible here. It's complicated enough already as it is. So we're restricting ourselves to commutative rings when we talk about zero-divisors. An integral domain has nothing to do with calculus, first of all. It has more to do with integers. An integral domain is a commutative ring with unity that has no zero-divisors. Probably should have said which has no zero-divisors. Theorem. The multiplicative cancellation law holds an integral domain. Note, of course, the cancelled factor must be non-zero. You can prove, and you should be able to prove, with a pretty quick proof that might be a little tricky, but I think you can get it. If R is an integral domain, with 3 elements A, B, and C in the ring, in the integral domain, and A not being 0, then AB equals AC implies B equals C. You can cancel the A's. This works, for example, with, well, never mind. I was going to say something, but I should not say it. Okay? You can prove that even without A, B, or C being units. Even without A being a unit. Its inverse, multiplicative inverse, doesn't have to exist. Don't multiply both sides of this by A inverse to prove it. That's an invalid proof, because A inverse might not exist. You can use the fact that it's got no zero divisors, and you can use the distributive law, is what you end up needing. A field is a commutative ring with unity in which every non-zero element is a unit. A field is a commutative ring with unity in which every non-zero element is a unit. You take away 0, you're left with a group under multiplication in a field. Or an abelian group under multiplication. There are actually things that are almost fields that are not commutative rings. They're called division algebras. We don't talk about those. A field is a commutative ring with unity in which every non-zero element is a unit. Every non-zero element has a multiplicative inverse, like the rationals, or the reals, or the complexes. Those are all fields. Q adjoining square root of 2 turns out to be a field as well. As does ZP when P is prime. Every field is an integral domain, by the way. Every field will have no zero divisors. Because if A and B are non-zero and this equation is true, well, okay, if you assume this equation is true and you assume A is non-zero, for example, you could multiply both sides on the left by A inverse and get the fact that B would have to be 0. That equation would be true. If that equation is true and one of the factors is non-zero, the other factor would have to be 0. That would prove the field is an integral domain. But not all integral domains are fields. Z, for example, is the most simple integral domain, you might say, infinite one at least. But it's not a field. 2 doesn't have a multiplicative inverse in Z, for example. Remember that first day of class? I said the main topics of our class are groups, rings, and fields. I had a picture of a group of people. I had a ring, the one ring from Lord of the Rings, and a field. All right, we've defined group, rings, and fields. We're done. Semester's over. No, plenty to do still. Fields have every property you might possibly want in an algebraic structure with 2 operations. Very quickly, 1 minute here, more on the integral domains and fields, some facts here. All fields are integral domains. The integers form an integral domain, but not a field. There are other examples too. If n is bigger than 1, Zn forms a field infinitely if n is prime, like I mentioned here. The rational numbers, the real numbers, and the complex numbers form fields, as does the rationals with square root of 2 adjoined. And another theorem is that any finite integral domain actually is a field. So actually showing ZP as a field, you first show that it's an integral domain, and then you use a more abstract theorem that any finite integral domain is a field. It's also a field. And that's it. Have a good day.